Hello everyone, my name is Sven Dittus and I'm a software engineer and expert for advanced robotics at ArtiMinds. In the next minutes I'm going to present the results of our approach on how to localize and track user-defined points on deformable objects for robotic manipulation. Manipulating deformable objects requires localization and tracking of points, which can be very challenging. Many state-of-the-art solutions are addressing this issue, but still have drawbacks. Some approaches are limited to specific materials, geometries, or distinct features. Others focus on reconstruction rather than tracking, and doing this online means no points can be defined by the user prior to execution. And then there are also solutions that suffer from insufficient precision or require markers on the object, with either one making them not applicable for most automation processes. Our contribution is a very generic approach that is geometry independent and doesn't require material modeling or learning. We propose a representation in which the resolution of the surface and the deformation are independent of each other. This allows to use a highly detailed surface model, leading to high precision, and a coarse deformation model, allowing for efficient computation. The model and the points of interest can be defined offline, which makes it especially suitable for automation processes, because no manual action needs to be performed during the execution time. We implemented a processing pipeline that works in an iterative manner to estimate the object's deformation from each observation. Knowing the object's deformation state then allows for tracking user-defined points on the object. In an offline procedure, the user demonstrates the model and the points of interest, and existing approaches usually struggle with large initial deformations. And we address this issue by demonstrating the object in multiple deformation states, which are then combined in a so-called object library. This only has to be done once for a new type of object. During the online execution, the deformation estimation is initialized with the most similar model from the library. For every iteration of the tracking pipeline, we preprocess a point cloud from the 3D camera by removing outliers and segmenting the object from the environment. In a second step, we identify correspondences between the deformed virtual model and the current observation. For this, we use commonly known projective correspondences, point-to-plane correspondences, and feature matching with a shot descriptor. Knowing these correspondences is the input for defining a nonlinear optimization problem, which tries to minimize the distance between the found correspondences. And additionally, we use a regularization term for the occluded areas of the object for which we can't find correspondences. The regularization term is a commonly used as rigid as possible approach. The first step of our solver is to do a position update, which is a classic rigid registration. And then we leverage a flip-flop solver structure to minimize the prior defined error terms in an iterative manner. Once the solver converges, the next depth image from the camera is processed, and we continue with the next estimation loop. To close the perception action loop, we integrated an interface through which a robot can request the pose of a certain point at any time. And by calibrating the camera system against the robot, the manipulation task can be executed. But enough of the theory now. Of course, we've tested our solution on an actual robot, which can be seen in the video here. The deformed object is placed into the scene at a random position, a scan is performed, and the best matching model from the library is chosen to initialize the tracking algorithm. Now that the algorithm is initialized, a robot equipped with a measuring tip can move to the user-defined point. The algorithm is executed on simple consumer hardware, and it takes about 1.5 seconds to estimate the deformation. The entire algorithm can be parallelized on a GPU to improve computation time and achieve higher frequencies. This is subject to our future research. Now that the object is moved to a different position, you can see that the user-defined point is again detected very precisely. The average precision we determined in our experiments was 2 millimeters with a relative deformation of 20% with respect to the reference model. In the next step, you can see another deformation being applied, and in the upper corner, a visualization of the converging algorithm. Once the deformation is estimated, the robot can begin with the manipulation. And of course, also a rigid and a non-rigid transformation can be detected at the same time within a single step. So now you see the camera taking another picture, the algorithm is converging and estimating the deformation, and the robot moves to the manipulation spot. For future research, we plan on optimizing our algorithm even further and also benchmark it against public data sets. For today, this is it. I thank you for your attention.